Have you ever stopped to think about what a logical proof really is? I mean, not just the symbols and steps on a page, but what it all fundamentally means. It sounds kind of simple, right? But it turns out to be one of the deepest questions you can ask in logic, philosophy, and, get this, even computer science. So let's dive in. We're going to see how we go from just a list of rules to a whole world of meaning.
Okay, so here's our game plan for today. We'll start with the basic idea of meaning itself. Then we'll check out a powerful concept called proof-theoretic semantics. After that, we'll see how a kind of mathematical blueprint helps us map it all out, what that blueprint actually shows us about proofs, and finally, and this is the cool part, we'll see how all of this connects to the actual code running on your computer as we speak.
All right, first things first. Before we get into the really heavy stuff, let's ground ourselves with the one simple but really profound puzzle that kicks this whole thing off. It really all boils down to this one question. Think about it. If you and I both prove the same theorem, but say my proof takes 10 steps and yours takes 12 slightly different ones, did we make the same proof? Do they mean the same thing? This isn't just a philosophical thought experiment. It's a huge challenge in logic known as the identity of deductions.
And here's what that looks like in practice. On the left and right, we have two different ways to prove the same thing. Both are totally valid, they get to the same conclusion, but you can just see they're shaped differently. The flow is different. And this gets to the very heart of the question. Are these just two different roads leading to the same city, or are they two completely different journeys, each with its own unique meaning?
To even begin to answer that, we actually need a totally new way of thinking about meaning itself. And this brings us to a really powerful idea called proof-theoretic semantics. So usually we think the word "and" gets its meaning from, connecting things out in the real world. But proof-theoretic semantics, or PTS for short, it flips that idea on its head. It says the meaning of a logical term, like "and," doesn't come from what it points to, but from how we're allowed to use it. The meaning is baked into the rules of the game.
The best analogy here is chess. What makes a queen a queen? It's not the piece of wood or plastic, right? It's her moves. The fact that she could zip across the board in any direction. Her entire identity, her queenness, is defined by the rules. Well, in this framework, it's exactly the same for logical ideas.
So what we're really doing here is creating a kind of grammar for logic. Meaning is all about use. The focus just shifts from asking, is this statement true, to asking, how does this piece work? What can it do? And the specific rules that define these moves, they've got a fancy name, canonical derivability conditions. They aren't just rules for a term, they are its meaning. Now, if you're going to describe this super complex grammar of rules and relationships, you need a special kind of language, a master blueprint, really. And that is where category theory enters the picture. Think of category theory as the mathematics of structure itself. It's way less concerned with the individual statements and way more interested in the connections between them, the transformations, the overall architecture of the system. It is the perfect tool for mapping out this world that proof-theoretic semantics has uncovered. And that's the key shift in perspective. Logic is no longer just a static collection of facts. It's this dynamic, interconnected web. Category theory gives us the precise mathematical language we need to describe this whole web of relationships and transformations. So, what happens when we take this powerful blueprint and apply it to our proofs? What new things does it show us about what they really are?
Okay, so traditionally we think of a proof as a simple linear journey. You start with your premises, you apply a rule, and you land on a conclusion. Step by step, pretty straightforward.
But here's where things get a little mind-bending. Category theory looks at that entire journey, from start to finish, and it sees it as one single thing. Not a sequence of steps, but one holistic transformation. It's called an arrow, and it points from your start point to your end point, representing the entire proof as one complete object.
And this brings us right back to our very first question. Because, let's be honest, a huge problem in this field is figuring out exactly when two of these journeys, two of these deductions, can be considered the same.
And this is where that blueprint really pays off. Category theory hands us this incredible tool called isomorphism. It's a mathematically rock-solid way to check if two of those arrows, two proofs, have the exact same underlying structure, even if the steps on the page look totally different. It actually solves the identity problem.
And on top of that, this structural view helps keep our logic systems, sane. It lets us check for something called logical harmony, making sure our rules fit together nicely and don't lead to crazy paradoxes. It stops us from inventing things like the infamous tonk operator, which was a logical rule so broken you could use it to prove absolutely anything. Yeah, not ideal.
Okay, this is all fascinating stuff for logicians, but why should the rest of us care? Well, it's because this very abstract world of proofs has a shocking and profoundly important connection to the technology that runs our world.
Seriously, get ready for this. It turns out that the entire structure of logical proofs that we've just been mapping out has a perfect mirror image in the world of computer programming. This beautiful connection has a name, the Curry-Howard isomorphism. And it's just so elegant. In logic, we have a proposition. In programming, we have a data type. A proof of that proposition, that corresponds directly to a functioning computer program. And every single step of deduction in that proof, that maps perfectly to applying a function in the code.
It is a perfect one-to-one mapping. And let me be clear, this isn't just a metaphor. It's not like a program. A valid proof is a working program. A working program is a valid proof. They are, at a deep structural level, the same exact thing.
And this just changes everything. It means a proof isn't just a static check for truth, it's a dynamic, computational process. Understanding the deep structure of proofs, their identity, their harmony, it directly helps us design more robust, more reliable, and more powerful software. We are literally programming with logic itself.
Which leaves us with one final fascinating question to chew on. We've just seen that a proof is a program. So when you or I sit down and reason our way through a problem, building an argument step by step in our heads, what exactly are we computing? What program is running inside our own minds?